welcome back everybody to our series on PixInsight. Well, let me start first by saying the weather has been atrocious. November was a complete blowout, totally wet, mild, and I can say that December has started exactly the same way, so even planetary imaging hasn't been possible. I was hoping for it to get cold, because at least you can dress for the cold, and when it's cold, you normally get nice, clear nights. But unfortunately, we're stuck with this horrible, wet, mild winter yet again. So, welcome back to this series we're doing on PixInsight. Today, we're going to look at the weighted batch processor. But before we get there, what we're going to do things manually. The best way to really understand what's going on under the hood of the weighted batch processor is just for me to give you a glimpse at how you can actually stack your images manually using PixInsight. So we'll first cover two applications, image registration and image integration, and we'll go through them first before looking at the weighted batch processor. So without further ado, let's start stacking something manually. Now, I prepared my images from last time. These are the same images you've seen already on NGC 331. As you know, we finished our last video where we've filtered out all the bad subs from the stack. So we've essentially cleaned our stacks and made them in the best possible condition to now go forward with the image registration. I'm not going to register all of them manually. I'm just going to take you through the process for the red images. So what you can see that I've done with the red images is I've already got here a folder at the bottom called Reg for registration, because the first thing you've got to do with these images now is to register them. Of course, over the night, our imaging platforms, our mount in particular, will track the night sky, and we will have feedback probably from a off-axis guider or a guide scope. It doesn't matter how you do that to correct those minor errors, but still, even if when everything goes very well, you will have minor tracking errors in your images. Also, you may be taking advantage of dithering, so that'll be adjusting the mount a few pixels up, down, left or right during the course of an image run to make sure that any systematic noise is not stacking on top of itself. And we can cover dithering as a topic in more detail later. So in any case, what you will have is minor alignment issues between image to image, basically from distortion from the atmosphere, from minor tracking errors, and of course if you're inserting any dithers into your imaging. So first of all, we have to align those images. So we go down here to image registration. You can see star alignment. If you click on star alignment, it will open the tool for you. And what we're simply going to do is we're going to go to our folder. We're going to add all the files that we want to align. So I have to navigate there. We go to the red and we say, okay, these are all the files that we want to register. Select them all and say open. But now we remember before we have to set a registration image or a reference image, and that's the file that we also discovered when we were cleaning the stack. And mine was 2025, which 2024 down here is one of the last ones in the second night running where I had the best image. Now we have to set an output directory, and we're going to set the red registered folder that I've already set up as the output directory, and it's that simple. And now I'm going to say run. Now, of course, I'm not going to make you sit through all this, even with this fast iMac that I have. I'll speed this up and we'll get to the point now where we come to stack the images together. So when we go back to the red folder, we can now see our registered folder, and we can see in there we have all our registered images, and we even have drizzle files. Okay, perfect. So now we've done the star alignment. Put this over here for now. Now we can go to the image registration. image integration. Let's do image integration. Now, image integration is also quite a complex dialog, but essentially what you're going to go over to is that registered images and add those files. I'm just going to do a Control-A or Command-A here on the Apple. That sets them all. I'm going to clear drizzle files and then say add drizzle files. I just clear it just in case there was something from a previous stack. I'm going to add them so they're all there ready to go. Now I could just press go, and I think perhaps I should do that, but there are some dialogues here. You can have a simple average, you can have the medium or min max. I stick to average, although there's very little difference between the median and the average, although statistically of course there is. Normalization, I leave that alone, and the weights, I leave them also alone for now. The weights will become more important with the weighted batch processor, but for now we can leave them be. But interestingly, we have no pixel rejection, and I'm going to leave no pixel rejection off for now. That's a little bit of a sin, and we'll see why, and I'll stack the image. Just press go. And in a moment, again, I'll speed this up a little for you in the video. We will have the integrated image. Now, we have a low, which is for low or cold pixels, and then we have our image. And here is our integrated image. Now, what's going on here? Well, you can see we've got some tracking from satellites and other issues. The image is particularly great quality because of the nights I've been imaging on, but you can also see some hot pixels here that haven't been calibrated out. You can see them more obviously over here. So this is actually, it's not a great image. In fact, what I would say is what we've just done is stacked an image as I would have done perhaps in the early 2000s when we didn't have all these beautiful statistical tools available to us. So let's now restack this image again. I'm going to close this one because, well, I don't like it for a start, and I've got lots of calibration problems here in this image because I just simply stacked it and everything's added up. So I'm going to close that and let's change that. Let's fix that now. The reason for doing this, by the way, is I want to show you what's going on under the hood of the script, the weighted batch processing. One of the big things that changed in stacking images is the ability to reject pixels. And one of the best functions, or it's the only function I use, there is a new function, but I don't use it just yet because I've never been let down by Winsorized Sigma Clipping. So we're going to put Winsorized Sigma Clipping on. We're actually not going to touch any of the defaults. We're going to leave it be. Neither are we going to touch any of the high or low, but here, if I do touch anything, it'll be the Sigma low or Sigma high, and this will just change the amount of pixels that are rejected. So those two sliders are the only ones that I really touch. I leave the Windsor cutoff alone for now, and let's stack that image again and see what happens. And what you will see is we'll see something magical. So now we have a rejection high. So these pixels have been rejected, and look at that. It's rejected the satellite tracks and that plane hit that was actually deliberately put back in to show you this. So they have been rejected as high values that are not image values. Then we have the low, and again we don't have a great deal of problems here with low or cold pixels. And now we have the image itself, and this is a much more acceptable or usable image straight out of the box, straight after registration. But this image has had literally no calibration applied to it. So no bias, no flats, nothing. Yeah, it's turned out pretty nice. Well, there's some optical defects there as well, but we can fix that with flats. So in a pinch, I will actually stack my images like this just to see where I am with my image stack how good it is, whether it's getting to whether or not we're getting to an acceptable image, I will do a quick test like this just to see where we are. And let's also do use the other tool that we like so much. Let's go to Blur Exterminator, and let's have a look at how it can tidy up some of my stars. There it is. Sorry, I have a widescreen monitor. My old monitor died, and some of the tools are dropping off the other side of the monitor, so I'll just pull that back on. As you know, the first step that I do here is correction only. So let's just do a correction only blur exterminator on this mono image of the red channel and see how it tidies up my stars, which are not too bad, by the way, considering it's coming from an RC which is completely oversampled in very poor Dutch skies. But yeah, there you go. That has tidied the stars up again really nicely. And you know, you could put a decent image together by just manually stacking your data, no problem at all. Okay, so what we just did was a quick manual stack of the red channel. Now, I'm not suggesting that you do that. So what you can see here now on the screen is the calibration frames that you will also endeavor to take to make sure that you can calibrate your camera. Now, normally it would be easy for me to say to you that to calibrate your camera, your images, you need to take 3 frames, but that isn't always true today. With my ZWO 1600mm Pro, I have to take 3 frames. Those are the dark frame, the master dark, which is a combination of 16 plus frames, the median of all those frames. And that records the dark current, the amount of noise that builds up over time as you're taking a particular subframe. Ideally, your master dark should match the length of your image frame. So if you're taking 120-second images of the night sky, then ideally you would have master darks that would be the same length, the same time. Now, there is a way for when you take biases to compensate or optimize your dark if you don't have the exact master darks for that imaging time, but I would recommend that you do and avoid the unnecessary complexity of calculating an optimized dark. So you then have a master bias. Now, a master bias, there's a little bit of confusion over the bias frames, and the bias frames are what I call a pedestal. So when you set your camera up, you have 2 basic values that you set for your camera. You set the gain of the camera, which determines how many electrons equals 1 photon. Ideally, you want unity gain there, so 1 electron is knocked off equals 1 photon, 1 ADU. Unity gain is the best to have, of course, but depending on the camera, you lose a little bit of dynamic range depending how you set the gain. But the other item you set in your camera is called offset, and that affects the bias. Basically, the offset lifts from 0 the beginning of the measured value, and that's because we don't want to have any negative numbers. Ideally, when you finish your calibration process, you want to have a image frame that contains only positive numbers, no negative numbers, and that's effectively what the offset is for. But the bias also measures, let's say, some shot noise or systematic noise that's in the camera. So you've got now the dark current, you've got some of the shot noise, which is also lifted with that pedestal to avoid negative numbers. And then you've got the master flat, and the flat records all the optical defects that are in your imaging train. And of course, this means it has to be taken, the flats need to be taken, preferably the morning after or the evening before, depending if you need to use t-shirt flats or whatever, before your images are run, so that you are recording the optical system as close as possible as to the date and time when you took the images, so that there's no more dust settled on the sensor, for example. The camera's not been rotated or changed position. Everything is exactly as it was, and the master flat will record all the optical defects, vignetting, the hot spot in the center, the dust motes. Everything will be according to the way the images were taken, and that's the best possible master flat you can take. But the mathematical operations, if you think about this, your image contains shot noise, it contains dark current, and it contains optical defects. Now, the mathematical operations here are pretty simple, except conceptually when you come to the flat. You want to remove or eliminate the dark current. That's the dark frame, so that's a minus. You want to remove or eliminate both the pedestal and any systematic noise or shot noise. That's the bias. And finally, you want to flatten the image with the master flat, and that is a division function. I'll try and put an image up here now, how you can visualize or conceptually realize what the master flat is doing for you. So that's essentially why you need these 3 calibration frames. However, if you have one of the newer sensors, you'll probably be doing dark flats. So just making sure your bias and your flats are shot at the same length and taking the bias away from the flats, because the amp glow or the dark current that used to be prevalent in a lot of CCDs and still some CMOS sensors is now going away, especially depending on what camera you've got. And I would recommend that, if you're uncertain of this, test your camera, put it in a dark place, lower it to your shooting temperature, wherever that may be, -20 or -10 or 15, whatever you have it set at. Run a couple of master darks at your normal imaging times. I tend to use only a few imaging times, such as 120 seconds, 300 seconds is my max, such as 60, 120, and 300 seconds. I never go longer than 300 seconds. My imaging times, like yours, will be basically limited by the sky glow. If you're in a dark area and you can go to 10 minutes, 600 seconds, great, all power to you. But again, even in those conditions, when I go to France, to Provence, I choose to stick at my maximum length of 300 seconds. 1, because I have darks for that, and 2, because I'm not willing to throw away a subframe longer than 5 minutes, than 300 seconds. There's also another important reason why I want to have more frames than more time, and we'll come to that in a moment. Okay, I started to make a controversial statement, or maybe a surprising statement. Maybe for some of you it's not so surprising. I started to say that I'd rather have more subframes than more time. So I'd sooner rather stick with a subframe length of, let's say, 120 seconds and get 50 of them in the night than go up to 300 seconds and only manage to get maybe 16 to 20 of them. Because I know that getting more subframes helps. How does it help? Well, it helps because of statistics. Now we're getting to the really dark, murky waters of statistics. Remember, what is it they say? Lies, damned lies, and statistics. Well, hopefully after this, I hope to prove to you that there are just damn liars that don't know how to use statistics. I thought about many things to try to bring this over to you. I thought about firing a full deck of cards at the camera and asking you to find the odd card out. But in the end, the one solution that I settled on was a dice roll, rolling dice. Now, I'm not going to roll dice here 1 million times to simulate, let's say, 1 million subframes. But what I can do, I can write a nice little Python program to do it for us. And what will happen, or what do you think will happen when you roll 4 dice 1 million times? So 4 dice work very nicely to make this Gaussian distribution. And what we're going to do, we're going to roll those dice now. And here we go. And we get a lovely natural normal distribution, which we discussed in the past, remember, when we looked at our data using subframe selector. And I put those lines in for you. The red line in the middle there is the mean. And you can see the 2 sigma, the two green lines, where 68% of our data lies. And then you can see the 95%, the 4 sigma or 2 sigma either side, the orange lines, where 95% of our data lies. But what's the purpose of this graph? Well, if you look at it, you can see that, well, if you roll 4 dice, the probability of rolling a 4 is 1/6 times 1/6 times 1/6 times 1/6. It's very low probability. Likewise, the probability of rolling 24, 6, 6, and a 6, and another 6. So there are very few 4s and 24s. But what you nicely see is that in the middle there, you see the peak of the distribution is around the number 14, which you can really come to quite easily with just using a bit of common sense. Of all these dice rolls, the combinations in the middle are the easiest to roll because there's more combinations that make up those numbers, so you get this lovely normal distribution. Now, what I want you to really realize here is there's no chance of rolling 1. That's impossible. The minimum number you can roll is a 4. And there's no chance of rolling 25, even though you see it there on the graph. There's no bucket above the 25, it's 24. There's no chance of doing that. Think about this as your imaging subs, and the bulk of your, let's say, brightness of your image, let's say your galaxy is, in my case, is the center of that distribution. It would actually be a Poisson distribution, which has a slight tail off, but this will do for now. So the center, the normal brightness or the main image of your image falls in the middle of this normal distribution. And the low end, the low darkness, low values falls off on the left-hand side to the number 4, and the highest, brightest star that possibly could be in your image falls on the right-hand side to the number 24. What cannot happen is that you have a 27 or a 28 or a 1. Not with all this data. That's impossible. You can see it now here clearly on the screen. This is where the Winsorized Sigma Clip and the Sigma Clipping comes in. This is how, or why I will tell you plainly and clearly right now, I prefer to have more subframes of a lower time than fewer subframes of a higher time. That means, as I said to you, I prefer to have 50 120-second subframes over 16 5-minute subframes, because the more subframes I have, the better these statistics works. That's how the Winsorized Sigma Clipping can eliminate the satellite tracks or the plane hits from your data, because as it goes through analyzing each and every one of your subframes, it sees the darkness surrounding your image. Well, it doesn't perceive it, but it sees the data as pure data. So if suddenly there's a bright track running through an image, or one image, 1 in 150, that is a satellite hit or a plane hit, it can immediately say, okay, this is not data. This is not what I recognize to be the data from this image session. So I can safely eliminate this. And what it does when it eliminates this, it says, okay, I look at the surrounding pixels around that track in the image, and I'll calculate the mean of those pixels from the other 49 that don't have the satellite track hitting them. And I'll replace the satellite track with the mean of the data from the other subframes. So the more subframes you have, again, as long as they're capturing the image data you need it to capture, so the more subframes you have, the better these statistics work. Now, at what point do you apply these statistics? After you've calibrated the images. And this is where the weighted batch processor, where its magic comes in. So without further ado, let's move on. Excuse me. So without further ado, let's move on to the weighted batch processor. Right, so let's go and open the weighted batch imaging. So if you look at batch processing under PixInsight, and you come down to weighted batch processing. There it is. There's the weighted batch processing script. This script has gone through many iterations over many years. It's a fantastic script, and it's a way of organizing or putting your images together in this script to allow this to all run for you automatically. We'll go through some of the buttons one by one. You've got your bias frames, your dark frames, flats, lights. Then you've got the calibration, how it's going to run. And we can check through that once we start to load up the frames. But I tend to use the buttons at the bottom. So let's add the lights to this. So now we need to go to our lights, which for me are over here. And we'll go to red. Control A. Open. So that's the reds added. I'll hit lights again. And this is another thing you can do. I've set mine up in folders, but you could set yours up all in one folder, the red, green, and the blue, because it will sort them for you, as you can see now. So there's the reds, and there are the blues. Let's add finally the green. It's just an old habit of mine to separate them into the folders. Also, it helps if I want to manually stack them with just the one registered. And you can see there's an unequal number of each. So I've got 45 blue, 39 green, and 46 red files. So that's my lights added to the weighted batch processor. Now, let's go to the flats. And the flats, just touch the flat button, go back here, and you can see that with the flats, I lumped them all in together. So that's the flats for all three filters. And you can see them here. So we've got 24 frames for blue, green, and red. That's the flats added. Darks. Let's add our dark library. Now I think I only found a limited library here. Yes, I did. So this isn't the complete library, but it's good enough for demonstration. So 16 frames, so you can see I'm sticking to those square numbers. And then let's go to the bias and add our bias frames, which again I put all together here in this map. And again, I think you'll find that's another 16 bias frames. And they're all, again, this is another important point which I didn't mention, so let's touch on it now. When you're building up your libraries, your calibration frames, you need to build them up in the same binning that you took the image. Now and that's probably why this is a limited set, because I'm binning with the RC. Normally with my other telescopes, because they're shorter focal length, I wouldn't bin. But with the RC, and because I'm so way oversampled, I'm binning here. So you can see my bias frames are bin 2, my darks are bin 2, as will be my flats. They'll all be bin 2, as are also the lights themselves. So you need to make sure your calibration frames match your light frames, preferably shot with the same times. Let's check the darks, 120 seconds, and the lights are all 120 seconds. So everything matches there, so there's no need to optimize or have an optimized dark here. Everything should work as is perfectly. Okay, the directory for the output of this has already been set, and everything is ready to go from here. But let's have a look a little bit under the hood of what's going to happen here. So you can see the frames are all lined up in the calibration. So they're going to make a master bias, a master dark, master flat for each one of the filters, and then of course you're going to get each one of the master lights made, the final image post calibration. So we're looking at an integration time here of around about 120 minutes on the lowest one there, with the 39 frames, which I think is red, which is the strongest channel anyway. And you can take a look at the pipeline. The pipeline is how it's going to run the process. It's going to run them in order. So there are 30 steps to running this. And you don't have to be concerned about this. But for example, it will now wait based upon the quality of the images, which images to give to use as the reference, which ones are the best images to stack the most of. It'll weight all that for you, and it's going to use the Winsorized Sigma clip. You can go back and see that. Let's have a look. It will use the Sigma clipping. You can set your weights here, image registration, integration. If you click on the integration cog, it can say automatically select its rejection algorithm, or here what I'm going to do is set Winsorized Sigma clip. This is the one that I like. It's never let me down. I've used it for most of the time. I've been using PixInsight. The new one, which I mentioned briefly, but I didn't tell you which one it was, is this generalized extreme studentized deviant. This is the new rejection algorithm. I find it a little bit too aggressive at the moment, and I fall back on the phrase, if it isn't broken, don't fix it. So I tend to stick to Winsorized Sigma clip here. You can leave it on auto if you wish. It's not a problem. I would select Winsorized Sigma clip. As for any, one moment, let me find it. There's a lot going on here with this script. That's why we did the manual stack first. I want you to realize that this is just a formal way of stacking your images automatically for you and applying the best possible processes to your images without any user intervention. But you can set your own presets, as I just showed you with the lights there. I've set the image, I've set Winsorized Sigma clip to be the rejection algorithm, because I prefer that. But also in the pipeline, depending on your camera, I don't know if you've got a lot of systematic noise, column or row defects, you can come over here and you can put on linear defects correction, and that may help you. Also, if you do have a camera, by the way, that is showing some systematic noise, some row or column defects, or column issues, best to dither, maybe dither aggressively, because the worst thing you can do is get them to align or stack on each other. If you can shift them around a bit, and it will help you to resolve potentially that issue. Finally, we have the post-calibration pipeline, and here you see you have a drizzle. I'm not going to drizzle this data. There's no point. I'm already completely oversampled. Okay, we're done. It took over 14 minutes and 8 seconds, just a little over 14 minutes. So let's close this, let's exit, and let's go and open the images. File open. Here we go back to our folder. What we should see now is a master. There's the master, and we have a auto crop red, green and blue, which are our filters, which I can now open. We can close the crop. There's our red. There is our green. And there is our blue. So let's give them an auto stretch. So you can see we still have gradients in there. As I said, these were taken on different nights. It's over 2 nights in November. And what we'll do, we'll leave it here for now. A weighted batch processor has done its job. It's calibrated the frames as best as it can. It's produced the images for us. And for our next video, which I'll try to get out before Christmas, but I'll make no promises there, because it is Christmas, the season to be jolly. So maybe it'll be in the new year. Just in case it is in the new year, I wish you all a Merry Christmas and a Happy New Year right now. But if I do see you again in the next video, the next video will be a little bit more controversial, because I'm going to change some terms or terminology which has existed for a while in astrophotography in processing these images, to give you, not just for the hell of it, but to give you a better understanding of what is happening when we process this data. And also, I'm going to ask you to be honest with yourselves in the next exciting video. Bye for now.